these are the notes for lesson 5.4, Complex and Imaginary Numbers, part 2. So this is the second part of 5.4. We're going to continue looking at imaginary numbers and simplifying them. The first thing we're going to talk about is something called a conjugate, and we're going to need to know what a conjugate is in order to get rid of imaginary numbers from the denominator. So if you remember, we talked about square roots and how we cannot have them in the denominator of a fraction. The same is true with imaginary numbers. So before we talk about how to simplify that, we need to talk about what a conjugate is. So to find the conjugate of a binomial, which is two terms, we're going to switch the sign between the two terms. And that just simply means if it's positive or plus, you make it subtraction. If it's subtraction, you make it addition. So for example 1, we're going to give the conjugate of each. So for part A, we have A plus B. So again, all we're doing is switching the sign. So the conjugate of A plus B is A minus B. For part B, we have 2 plus 3i. Again, you're just changing your sign. So the conjugate is 2 minus 3i. For part C, we have 5 minus the square root of 2. So the conjugate would be 5 plus the square root of 2. And then lastly, for part D, we have 5 minus 6x. So the conjugate of that would be 5 plus 6x. So again, we're just switching the sign. So if it's subtraction, we change it to addition. If it's addition, we change it to subtraction. Now let's look at why conjugates are useful. So if you remember when we reviewed factoring, we looked at a plus b times a minus b. So we have factors that are the same. The only thing that's different is their signs. So one's positive, one's negative. So if we multiply this out, a times a is a squared. A times negative b is minus ab. A times b is plus ab. And b times negative b is minus b squared. And remember, this is one of those cases where our middle terms will cancel out, and we're just left with a squared minus b squared. So by multiplying by the conjugate, we can get rid of those middle terms so that we don't have those middle terms anymore. And you're going to see why that's important when we're looking at imaginary numbers in just a second. So conjugates allow us to do a couple of different things. The first one, it allows us to get rid of radicals in the denominator. It also allows us to get rid of imaginary numbers in the denominator. So we know that we can't have radicals or imaginary numbers because imaginary numbers are square roots or radicals. So we can't have either of those in the denominator, so we're going to use conjugates to get rid of them. So for example 2, we're going to write each expression as a complex number in standard form. Now it's important to remember that we always be sure to multiply the numerator and the denominator by the conjugate. So if we multiply either the numerator or denominator by something, we have to multiply by both in the numerator and the denominator, because that's like multiplying by 1. So for part A, we have 2 plus 3i over 4 minus 5i. Again, to get rid of that imaginary number in the denominator, we have to multiply by the conjugate. So I want you to think for a second and write down what the conjugate would be. If you said 4 plus 5i, you would be correct. So again, we're going to multiply by 4 plus 5i in both the numerator and the denominator. And then we're going to multiply it out. So we have 2 times 4 in the numerator, which is 8. I have 2 times 5i, which is 10i. Then I have 3i times 4, which is 12i. And lastly, 3i plus 5i is 15i squared. Then in the denominator, I'm going to do the same thing. 4 times 4 is 16. 4 times 5i is plus 20i. Negative 5i times 4 is minus 20i. And negative 5i times a positive 5i is a negative 25i squared. So now we can just simplify, combining like terms. So in the numerator, we have 8 plus 10i and 12i is 22i, plus 15 times I squared is a negative 1. In the denominator, we have 16 plus 20i minus 20i, and our i's are gone. So this is actually 16 minus 25 times I squared again is negative 1. So there's a little bit more simplifying we can do. In the numerator we have 8 plus 15 times negative 1. We know that 15 times negative 1 is a negative 15. So 8 and negative 15 is negative 7 plus 22i. And in the denominator we have negative 1 times a negative 25. So this is actually plus, so 16 plus 25, which is 41. So notice, by multiplying by the conjugate, we got rid of our I terms in the denominator. When we square I, we know that that's negative 1. So by, again, multiplying by the conjugate, we get rid of those middle terms, which contain our imaginary numbers, so that we can fully simplify without imaginary numbers in the denominator. So for part B, we have 1 over 3 plus 2i. Again, we're going to multiply by the conjugate. So I have times 3 minus 2i. Now in the numerator, I just have 1 times 3 minus 2i. 1 times 3 is 3. 1 times negative 2i is minus 2i. In the denominator, I have 3 times 3, which is 9. 3 times negative 2i, which is a negative 6i. Next I have 2i times 3, which is a positive 6i, and 2i times negative 2i, which is a negative 4i squared. So notice, again, our middle terms cancel out, so we get rid of our i's in the denominator. So we still have 3 minus 2i in the numerator, and 9 minus 4 times negative 1. So negative 4 times negative 1 is a positive. So this gives us 3 minus 2i over 13. Now another way we can write this, we actually need to write it like this in order to simplify if possible. So we can break it up like we've talked about before. So this is the same as 3 over 13 minus 2i over 13. So we can write it either way. However, we need to make sure that we split it apart if we can see that something can be simplified. So again, we multiply by the conjugate in order to get rid of our radicals or imaginary numbers in the denominator. One real-life example of complex numbers is fractal geometry. As you can see here, this is an example of a fractal. A fractal is sometimes known as a pattern of chaos. And these patterns of chaos, or fractals, are looked at in a lot of different areas, a lot of different professions. One is in engineering. The second is in science. So a lot of the time scientists will look at the fractal patterns of blood vessels and lungs and veins. So all those different patterns they will look at and look at different aspects of those. Another example is the stock market and astronomy. Fractals are also found in nature. So if we look at the veins or the parts of a leaf, different patterns in nature. And the last example I have for you is fluid mechanics. So there's a lot of different real-life applications or real-life careers that use fractal geometry. So to break fractal geometry down, we're going to graph in a complex plane, and we're going to talk about what that looks like. So we're going to plot the following points. So in your coordinate plane, the x-axis is going to be our real axis. Our y-axis is our imaginary axis. So when you're graphing, we first graph our real numbers. Those should be written first because we said that's standard form. So you're going to go left and right based on what your real number is, and then you're going to go up and down based on what your coefficient is with your I. So for part A, if we have 1 minus 2i, again start with your real number, which is a positive 1, so we're going to go over 1. And then we have minus 2i, so that would be a negative 2 on our imaginary axis. So we're going to go down 2. So our point for part A is right here. Part B, the same thing. So our real number is negative 2. So we're going to go to the left 2 because it's negative. We have a positive 3i, so we're going to go up 3. And our point for B is right there at negative 2, 3. For part C, we have 4i. Now notice we don't have an imaginary part, so this would be the same as saying 0 plus 4i. So we're not going to go left and right because we don't have any real part. We're just going to go up 4 on our imaginary axis. So this is C. And then lastly, part D, notice we just have the real number 4. So this is like saying 4 plus 0i. So in this case, we're going to go to the right 4. And we're not going to go up and down because we have no imaginary part. So this is D. So again, the only difference is that our x-axis is our real numbers, our y-axis is our imaginary numbers. Another application of complex numbers is looking at the absolute value. So if z equals a plus bi, so again that's an imaginary number in standard form, then the absolute value of z equals the square root of a squared plus b squared. And we're going to talk about what this means and what it looks like. The absolute value of a complex number is the number's distance from the origin in the complex plane. So if we look at the complex plane, again the x-axis is our real axis, the y is our imaginary. So if we graph a plus bi, so a is going to be on our real axis, and b is going to be on our imaginary axis. So to find our distance from the origin, we have to make a line or segment from this point AB back to the origin. Now if you look, we have a right triangle here. We know that if we know one side, or if we know both sides, we can take a squared plus b squared, and that will give us our c squared. So to solve for c, or to solve from the distance to the origin, we have to take the square root of everything. So this c is equal to the square root of a squared plus b squared. So again, the absolute value of z is just like saying our c. So we find the absolute value of z by finding that distance from the origin by using the Pythagorean theorem. Example 2 says to find the absolute value of each complex number. So part A says 3 plus 4i. Remember the x-axis is our real axis and y is imaginary. So if we are to graph this, we're going to go to the right 3. We're going to go up 4. And again, find the absolute value, we're finding the distance from the origin. So we're finding the length of our hypotenuse in this right triangle. So we're going to find 3 squared plus 4 squared. And remember, we're going to take the square root of that. So 3 squared is 9. 4 squared is 16. 9 and 16 is 25. And the square root of 25 is 5. So the absolute value of 3 plus 4i is 5. Part B, we're finding the absolute value of negative 3i. So again, if we start at the origin, now notice there's no real part to this complex number. So this is 0 minus 3i. So we're not going left and right, we're just going to go down 3. So again, if we set it up, we're not going left and right, so that's 0 squared plus negative 3 squared. And again, we're taking the square root of that. So this equals 0, the square root of 0 plus 9, which is just the square root of 9, which is just 3. Now for this one, since we don't have a real part, we could have just counted our units, and we know that our distance is 3 from 0, or 3 from the origin, so our answer is just 3. And lastly, for part C, our real part is negative 1, so we're going to go left 1. Imaginary part is 5, so we're going to go up 5. And again, we're looking for the distance to the origin. So we're going to have negative 1 squared plus 5 squared. We're taking the square root of that. So this is the square root of 1 plus 25, which is the square root of 26. Now this is where we set up our prime factorization. I can divide by 2, and that will give me 13. I can divide by 13, and that will give me my 1. Now notice there are any groups of 2. So the square root of 26 cannot be simplified. So it's just the square root of 26. So again, there are a lot of real-life applications for complex numbers when we look at the graphing aspect of it as far as fractals are concerned. And there are a lot of different careers that use fractals in complex numbers.